Welcome to the equilibrium composition. So let's look at the formation of dinitrogen tetroxide from nitrogen dioxide. So we have nitrogen dioxide, we have two of those molecules reacting together to give us N2O4, the dinitrogen tetroxide. So nitrogen dioxide, the reactant in this case, is a dark brown gas, but the dinitrogen tetroxide is colorless. So if we put some nitrogen dioxide into a flask and watch over time as it reacts to form our dinitrogen tetroxide, then over time our dark brown color fades as the reaction proceeds, but it never completely disappears, which means that the reaction never totally goes to completion. We never get rid of all of our NO2. We never get rid of all of our reactant. And why is that? Why does the reaction stop or appear to stop after a while? So again, this means that the NO2, the nitrogen dioxide, never reaches zero concentration. It never goes all the way away. And this is because the reverse reaction also occurs. We can have the dinitrogen tetroxide decompose to give us back some NO2. In this case, we're getting two of them. And if this reaction is occurring at all, that means we can't ever get rid of all of our NO2 because, well, if we get rid of most of the NO2, then most of what we have left is the N2O4, and now we've got a lot of our reactant in this reaction that can then give us the product, and that gives us our NO2 back again. And so that means that this reaction must be happening at least to some extent, because we're never getting rid of all of our NO2. So, at some point in the reaction, the rate of formation equals the rate of decomposition of our dinitrogen tetroxide, and now we've reached a chemical equilibrium. And note that in this equation where there's this box here, it's not displaying the character correctly, but we should have a double arrow, one pointing to the right and one pointing back to the left, showing that there are two processes occurring. And now we've reached an equilibrium. So we have the forward reaction going and the backward reaction going. They're at the same rate, and so the size of the two arrows is the same, or it's supposed to be, if I've drawn it correctly. So note here that the chemical equilibria are dynamic equilibria, which means that both processes are occurring. It's not the case that we've reached some point where nothing happens anymore. We do still have the forward reaction happening. We have two NO2 molecules combining together to give us our dinitrogen tetroxide, and we have some dinitrogen tetroxide molecules decomposing, going backwards to give us our two NO2 molecules, again, the nitrogen dioxide. And so if you look at the molecular scale, both reactions are happening. So the forward reaction of creating the dinitrogen tetroxide is still occurring. It's just that that backward reaction is balancing it out. So over time, we have no net change in concentration of reactants and products. So another way of looking at this is graphically. So we have reaction rate as a function of time, and here we have the forward reaction rate. So initially, that forward reaction, we have only reactants around, we don't have any products around, and so the forward reaction rate is very high, and over time, as that forward reaction occurs, we're lowering the concentration of NO2 that we have around, and that means that our forward reaction rate is going to drop, and it drops and drops and drops. But as the forward reaction rate, or as the forward reaction goes, our concentration of NO2 drops. That means our forward rate is decreasing. And if the reverse reaction never happens, then at some point the forward reaction rate reaches zero. It asymptotically approaches zero, at least. As our concentration gets smaller and smaller and smaller, the rate will slow down. But as we have that forward reaction occur, then the dinitrogen tetroxide, the N2O4 concentration goes up because that's the product of the forward reaction. And that means that now our reactant of the reverse reaction, the decomposition reaction, is getting more and more concentrated. As the reactant concentration gets higher, then that reaction rate gets higher. So over time, our reverse reaction rate gets higher. And at some point, then at this point here, those two reaction rates are equal. And at that point now, the rate of formation of N2O4 and the rate of decomposition, the reverse reaction here, the formation and decomposition rates are equal. And at that point now, there's no longer any net change because every time we have one N2O4 molecule be created, we have another one be destroyed, or at least it averages out that way over time. And so from here on, those reaction rates are the same. You note that they're non-zero. We haven't reached all the way down here, but both reactions are occurring, and that means that they're both balancing each other out. And so now we've reached equilibrium. So at this dotted line, anytime to the right of that dotted line, we're at equilibrium. Anytime to the left of that dotted line, we haven't yet reached equilibrium. So things are changing from the 0 time here up to this dotted line, and then we've reached equilibrium. And then there's no net change overall, even though if you look at any one individual molecule, it will change. It will go back and forth over time. But the whole composition of our entire flask isn't changing anymore. So that was the equilibrium composition.